The objective of this video is to introduce rotating circumferential current density created by polyphase windings. Up until now, we've been considering only a single phase at a time when we sketch a stator winding. In this video, we're going to show what happens when you have a three-phase winding that is excited by three-phase sinusoidal currents. And we're going to consider this by, again, talking about a circumferential current density, an equivalent circumferential current density, and talking about just a single harmonic component of it. So in a previous video, we talked about how we can represent a current density as being a sum of harmonic components. In this video, we're going to further distinguish the current density as belonging to an individual phase. We're going to call these phases U, V, and W. And we're going to look strictly at one harmonic of these phases. So let's start by sketching a stator and a rotor. And I've written an expression for the circumferential current density of phase U, the first phase. And you'll see that I've written it in terms of this value AC hat prime pH. All right, what does that mean? This is just a temporary thing that we're doing to try to clear up our notation in this video. And basically, we're trying to differentiate between the current circumferential current density of the total stator versus that of a single phase. So this pH means that this is the peak circumferential current density of a phase, and the prime here means that it's been divided by the phase current. And we're doing that because we're assuming that we're going to have the same winding, just displaced 120 degrees for each phase. So you can see I've written an expression for what this AC hat prime means. It's our peak circumferential current density divided by the current that is flowing in our coils. This is like a winding function, but it's not describing the current linkage. It's just describing the current density, but divided by the amount of current that's flowing in the coil. So basically, it's telling us where our turns are present on our bore of our stator. And we're adding this pH because we're talking about it for a single phase. So up above here where I wrote review, we can say that this is a circumferential current density of a single phase, and we've got these harmonics. It's a sum of these harmonics. Okay, so we have this expression for the circumferential current density of phase U, and as we've been talking about, for alpha equals 0, there's no ampere turns. Then as alpha departs away from 0, we slowly get more and more ampere turns, and it grows until we're peaking at 90 degrees and negative 90 degrees. And so we can say that this long line that I've drawn here coming out is our phase U axis. And next we'll sketch our phase V winding. And so the phase V winding is the same as a phase U winding, but it's shifted by 2 pi by 3. It's shifted by 120 degrees. And finally, we'll denote the phase W winding. And that's shifted by another 120 degrees, so by 240 degrees from phase U. And so I've drawn the conductors to be different size to represent the relative magnitude of the current at that location. This should be familiar to you from a previous video where we were using the Maxwell stress tensor to make force calculations, and we had a linear current density on the bore of our stator. This is a similar case here. We're now indicating this as a circumferential current density on the inner bore of our stator. And I've drawn these on different levels, and the outer ring is phase U, the middle ring is phase V in blue, and the inner ring is phase W in green. That doesn't really mean anything of significance. It's just to try to make the drawing clearer. This is an equivalent current density that is a single harmonic of the actual circumferential current density as we've been talking about in the previous videos. The next thing to point out for this is that we've got this variable n here, which is indicating our harmonic index. And the way I've sketched this right now is that n is equal to 1. If n was equal to 2, this would be showing 4 poles, and the pattern would have to repeat itself again. And you'll learn about this in your drives classes, but we can consider for typical machines, we consider them to be periodic over one electric period, or over 360 degrees electrically. And so in a drives class, in a control class, you would typically consider your motor to have you typically sketch the fields of your motor over 360 electrical degrees, which would be related to the mechanical radians or mechanical degrees based on what we learned about at the beginning of this class, which is the number of poles. So if you have a 4-pole rotor, you have 720 electrical degrees for one 360 mechanical degree span. Or if you have an 8-pole motor, you'd have 1,040 degrees per 360 degree mechanical span. Alright, so we've got our motor model sketched for these sinusoidal circumferential current densities, these equivalent current densities. I want to comment on the electrical connections. So we're setting up a situation that we're analyzing. So we've got our motor over here, and now let's talk about electrical connections. You can see that I've sketched our electrical hookups as having a neutral point. So this region in here is our electric motor. And the inductor symbol is representing how our phase windings are connected. They're connected to a neutral in the center. And with this connection style, by necessity, our currents have to sum to 0. There's only 3 connections. So Kirchhoff's current law says that the sum of all the currents entering a node have to be 0, and that has to be true here as well. In this case, we're going to assume, and in this class in general, we're going to assume that our currents are all balanced sinusoidal currents. So this phrase, we use 3-phase balanced sinusoidal currents. What does that mean? Well, that means that we can write an expression for our currents into the phase windings of our machine as follows. Our currents can be expressed as sinusoidal quantities with a constant magnitude of I hat, and the argument of the sinusoid, or the cosine, is omega t plus some phase angle phi I. And so phase V is delayed from phase U by 2 pi by 3, and phase W is delayed by phase U by 4 pi by 3. And this is the typical expression for 3-phased balanced sinusoidal currents. These are the currents that you want to see on your power grid, on your 3-phase power system connections. All right, the key things to take away from this is that we've got this expression for our circumferential current density on the inner bore of our stator, and we've got this expression for our currents. The total circumferential current density on the inner bore of our stator is actually going to be the sum of these 3 phase quantities. And so we've written out our expression as the sum of these 3 phase quantities, and we're going to just plug in these 3 expressions now and start to manipulate the equations. And so you'll see that we start off by writing our circumferential current densities for our phases as sinusoids, but down here I've written them as cosinusoids. The reason for this is that, or the reason I was able to do this is that I've subtracted off a negative pi by 2 from each quantity, which means we can express them as cosines. And you could write them as sines. This is just a style choice that I did this. And I want you to remember from, you're all electrical engineers, or most of you are, I want you to remember from your introductory courses, phasor analysis. The way that we like to deal with sinusoids as electrical engineers is express them as phasors. And so we said if we had this quantity here, a cosine with some argument gamma and amplitude a hat, it can be expressed as the real part of this quantity. So if we use that property, we can rewrite this in terms of phasor expressions. And those of you who've taken drives classes might recognize that this quantity in the square brackets is actually a quantity called your current space vector, but it's the conjugate of it. And so we can work on this quantity, but in order to go further, I need you to recall Euler's formula, which is that e to the j gamma is equal to cosine of gamma plus j times the sine of gamma. So if we use that in this expression, we can write it in terms of cosines and sines. And now we're ready to go up to our current expressions, that are these expressions right here, and plug them into our current derivation. So plugging our currents into the blue equation, we get this expression. And don't take my word for this. I want you to try this yourself. you should be able to go from the first blue equation to the second blue equation. It's something that you're going to see time and again in your power courses. And simplifying further, again, you should be able to do this on your own as well. You get this expression. We can now bring this back out to our full equation. And if we do that, we get the following, which we can evaluate as a sinusoid. And please try your hand at this. I skipped a few steps in this derivation, but I'm giving you the final result. I'd like you to practice this on your own. Get comfortable with this. So this expression that we've resulted in is pretty magical. This shows that we went from having these three distinct current densities excited by sinusoidal currents. We ended up creating an equivalent current density in the air gap that rotates with time. So we can write this expression, we can summarize this expression as follows. With our conclusion being that three-phase symmetric windings, polyphase windings, plus balanced sinusoidal currents give us a rotating circumferential current density, an equivalent rotating circumferential current density. And we can sketch a physical interpretation of this. As the following. And so in this case, you can see that we have a winding that's centered about this angle alpha w, where alpha w is this expression right here. That means that alpha w is rotating with time. It's increasing. Alpha w is traveling this way. And as time goes on, this whole winding rotates counterclockwise. Then we can also sketch this as a linear diagram. And we can summarize what we've observed and done here by saying that the full story is that we start with a motor with windings that are in slots, with coils that are in slots. So we've got windings or coils in slots of an electric motor. And from that we notice that we can express the circumferential current density of our winding as a harmonic series. And we can go from that to selecting a single frequency to work with, and then having three-phase distributed windings and exciting them with three-phase balanced sinusoidal currents. And from that we can make this observation that we end up with an equivalent rotating circumferential current density on the inner bore of our stator. So in summary, this video has introduced the concept of a rotating circumferential current density and shown how if you excite it with a balanced three-phase winding, you end up producing a rotating circumferential current density on the inner bore of your stator.